In today's lecture, I'd like to talk about situations where you have complex cash flows and have to do a calculation with these complex cash flows. We've seen in the past that we have some specific techniques for dealing with cash flows that follow a particular pattern, whether they are a future cash flow, an annuity, a gradient, a deferred gradient, and other non-standard annuities and gradients. But in real life, cash flows can be of an arbitrary nature, occurring at any point in time of any pattern. What we do in that case is to decompose a complex cash flow into a set of cash flows that follow the definitions we've given previously. I have an example here where Clem is saving for a car, and he's put the money in a bank account that pays 12% interest compounded monthly. We have a balance of $2,400 currently, and Clem's going to be saving $120 per month from his salary. And once every 4 months, he's adding $200 in dividends, and this money is accumulating in the account, and he's eventually going to save enough for the car. He also has bank fees of $10 per month, which are expected to increase by $1 per month henceforth. And the question is, how much will Clem have saved in 2 years? Now, it's kind of obvious that I've structured this problem to fit in with the cash flow patterns that you're familiar with. But in many ways, it's similar to a real problem, and there's a lot of components to it. Let me illustrate these components a little more graphically. Here's a cash flow line showing the 24 months involved in our problem. We have several different components to this problem. First of all, there's the money in the bank now. That's a present worth, illustrated graphically by this upward pointing arrow. We also have his $120 a month savings. This then is an annuity starting 1 month from now, spread over the 24-month period. We also have every 4 months the $200 in dividends. And finally, subtracting from these cash flows are the bank payments. Now, we see that this is a complex set of cash flows, and we put them together are very complicated. Now, in real problems, you tend to start with a complicated cash flow sequence like this and have to decompose it. And I've structured this problem so it's obvious that composition and decomposition process. But essentially, that's what we have to do with all complex problems involving a cash flow pattern, is to subtract from that cash flow the components that we can recognize and transform easily. We subtract from it a gradient. Transform the gradient to the desired amount, in this case a future worth, and do that calculation of the gradient alone. And then take out, for example, a non-standard annuity, do the calculation on that. Take out the standard annuity, do the calculation on that, and then whatever's left, whether it be a present worth in this case or other future worths, deal with them individually. In other words, decompose the problem into various components that we're familiar with. So in this case, what I would do is recognize we're looking for a future worth. And I'd break it down into several other future worths, depending on the different components of the problem I'm interested in. Say F1 plus F2 plus dot, dot, dot. And in this case, I believe you'll see in your notes that I have 8, that's F8, 8 positive components. That's the balance in the bank account, the salary annuity, and the non-standard annuity of dividends, which I treated as I think 6 different future amounts. And then subtracting from that the cost part, that's the gradient, as an F9. So each of these components, and this is kind of a general expression of it, except for the particular numbers I use, are the standard components we know how to change, be they annuities, gradients, or future or present worths. Now, I won't run over the calculation in this video in detail, but you'll see what we do in the notes is to calculate each of these future worths separately and then add them together for the total future worth. In this case, that total F then works out to be $7,026.21 as money saved. So it's a matter of decomposing those complex cash flows into simple components that you can then add together and add or subtract together. Not all complex problems are of the form of simply finding a future worth or present worth or something like that. There can be unknown interest rate or unknown number of periods problems too. Here's another example where the Easy Loan Company advertises a 10% loan. And the logic of their loan goes like this. Say you need to borrow $1,000. The idea is that 10% comes from paying back the $1,000 plus $100 interest, $100 being 10% of 1,000. And you pay that in 11 equal $100 amounts, starting 1 month from today. In addition to that payment, there's a $25 administration fee for the loan, payable immediately, and a processing fee of $10 per payment, and a $20 non-optional closing fee to be included in the last payment. What we want to know is the actual effective interest rate. So this is an unknown interest rate problem. We're given some information about the nature of the cash flows involved. And we're given some misleading information too, such as this 10% business. This 10% loan is just a name. As you'll see, it doesn't really mean very much at all. The key here is you're looking for an unknown interest rate. And so you want to create an expression in terms of that unknown interest rate. Now, the way we do this is to recognize that the amount of money you're getting is going to be equivalent to the amount of money you're paying. The amount of money you're getting is $1,000. Now, it's not exactly $1,000 because part of the problem is you're paying a $25 administration fee right now. So that's going to have to come from the money you're getting. So it's really minus $25. So it's $975 you're actually getting. Paying, well, you're paying a bunch of different things. You're paying the 11 equal $100 installments starting 1 month from now. So that's an annuity. And if we're going to be comparing that to what you're getting, the fair way to compare it is today. So we'll convert that payment into a present worth equivalent. So it would be the $100 times the series present worth factor at this unknown interest rate over the 11 periods. But you're paying more than that. You're also paying the $10 fee per payment. And you're also paying this $20 non-optional closing fee. So that's $20 in the future as a future amount brought back at the unknown interest rate over the 11 periods. So in order to calculate this unknown interest, we want to equate these two and solve for the unknown I. So the expression is 975 is equal to, now we can add this $100 and $10 together, so 110 plus that future worth amount. To solve this expression, well, the thing to do is to put everything on one side of the equal sign and solve for the other side. Now, in the way we've done this, well, probably the easier way to do it would is to switch the left and right-hand sides so that we've got like this. Now, so what we do is we take an arbitrary value of I. This is the easy way to do it. Take an arbitrary value of I and see whether it's above or below $975. For example, for I equals 4, the left-hand side is equal to 976.37. And for I equals 5, the left-hand side is equal to 925.37. So now I did some trial and error to find this I equals 4 and I equals 5. I'm showing you the results of that trial and error. But what we've done is we've bracketed that 975 target. Even though this is a fairly complicated expression, we could have 10 different components to this, depending on the components of the original problem. But as long as we have all the elements involved in this unknown I on the left-hand side, and we bracket the right-hand side, well, we can use linear interpolation to estimate a value that gives that exact value of 975 that we desire. We do that linear interpolation. Linear interpolation, we get the I of 4.03. Now note again that this is 4.03 percent per month. We're asking the problem for the effective interest rate. We use our effective interest rate formula to calculate the effective interest rate we get I is equal to 1 plus 0.0403 to the 12th, because we want to do it, of course, for a year, which is 12 months, minus 1, equals 60.69% effective interest. So the process here, as far as complex calculations go, is exactly the same as we do for any simple calculation involving unknown interest rate. It's just that the components of the expression that we're solving for the unknown I are a little more complicated. So it takes a little bit more work. Another thing in particular about this particular problem is you notice this is 60.69%, almost 61% interest for what's been called a 10% loan. And our intuition says, sure, it's a 10% loan because we pay 10% more. But we've got fees, we've got other things added into those costs, which really are interest, because interest is, in this context, is money paid for the use of borrowed money. So 60% interest is a pretty high interest rate, especially when you're told, in a sense, it's 10%. And if you like, that's a lesson, a real life lesson that is pretty important. And if you look very carefully at what you're actually paying for borrowed money, it's often quite a bit higher than it seems. Thank you.